Started now. Chitra, Max, and I would like to thank you for joining us this morning to learn about our data pipeline framework. And next slide. Before we start, we'd like to take a minute to acknowledge our sponsors, the Water Power Technologies Office and the MHKIT and PRIMRE projects, and our collaborators at NREL and Sandia, who we've worked closely with to identify requirements and use cases for our initial version and our data standards. This webinar is the second of a two-part series on data standardization. And the first webinar's recordings are available online, as will the recordings from this webinar. And all recipients or attendees will receive an email with a link to the recording once it's posted. Next slide. So what we'll talk about this morning, I'll quickly review our pipeline vision and recap then the data standards we discussed at our previous webinar. Then I'll give you an overview of the TS-DAP pipeline framework. Next, Max will give you a live demonstration of how to use the pipeline for a real data use case scenario. And finally, we'll conclude with a project roadmap and provide links for more information. And of course, we'll have a session to open up the floor for any questions. Next slide. So currently, it's difficult to answer overarching meta questions like, how do you compare the cost of energy across two different devices? So data is not easily accessible, and in addition, it's in a variety of formats, which makes it difficult to analyze. It involves a lot of data wrangling, which is costly and increases your time to market. So our vision is to provide an easy-to-use pipeline framework for converting time series data into standardized format, and then to utilize these pipelines in repositories such as the MHK data repository to provide integrated access, aggregation, transformation, and query capabilities that enable users to analyze data across multiple data sets and wide time ranges. We also want to ensure that the pipeline is domain agnostic so we can leverage contributions across projects. Next slide. So a quick recap of our data standards. We discussed that we'd start with a baseline set of data standards that could apply to any data set. And they include key concepts such as embedding metadata with the data, including provenance information about how the data was obtained, and data quality results, specifically adding data quality in bitwise QC flags. Specifying a standard set of units, standard names for variables, and standard file formats and naming conventions so that file names are self-documenting and easy to find. We identified also, in addition to the baseline standards, we identified the need to describe specific data models to extend the baseline standards, and they are tailored for a specific type of data, such as wave energy converter field testing. Note, we still need to define data models for the marine energy community. So what we're starting with right now and in our demo today are just the baseline standards. We hope that over the next year or two, we'll be able to define a lot more. And we'll work closely with the MHKDR to define these data models. All right, next slide. So now I'll give a quick overview of the types of pipelines that we have that our framework will support. So the first type of pipeline is called an ingest, and that is used to convert raw data into a standardized format. The standardized format is for an ingest is referred to as an A data level. So it's gone through the first level of processing. And then the raw data we usually refer to that as a 0 data level, because nothing's happened to it yet. And then the next type of pipeline is a higher order pipeline. That's called a VAP, or a value added product. And the purpose of that is to aggregate, transform, and or summarize multiple lower level data streams. And they also can be used to add algorithms to convert lower level measurements into more meaningful scientific properties. So VAP data is called a B data level, and the higher the data level, that just indicates the more processing has occurred. And like I said, for this first release, we're only going to be supporting ingest pipelines. And then it's our future next fiscal year task to implement VAP support. Okay, next slide. So now I'll give you a quick overview of all the components of our TSDAT ingest pipeline. So our framework is called TSDAT for Time Series Data Pipelines. It is written in Python, and thank you. And it uses the popular Xarray dataset library for working with datasets of any size or shape. The high-level steps of the pipeline, as shown, are to first read the raw data, then convert it to standardized format. That includes converting data types, renaming variables, etc. Then we perform quality control, quality assurance checks and record the data quality results. And finally, we save the processed data set and any supplemental files like plots to a specified storage file system, such as local storage or AWS. Note that the pipeline currently is one file in, one file out, but later we will add the ability to process additional formats besides just files. So like messages, so that we can support records in like a near real-time streaming framework. And then when we add the VAP capability, we'll have the ability to add aggregate summary files like the summary per day or summary per week. So next animation, thanks. So in order to control exactly what runs in your pipeline, we have two different configuration files that the users can fill out. The first one is the pipeline config. That defines the variables you want to include from the raw data files, what units you want to convert to, what metadata you're going to include, and what QC checks to perform, etc. And then the storage config file, that identifies which file handlers you want to use to be able to read and write your data, since that is all variable. You can write to any format that you have a file handler for. And it also identifies where to store your processed data. Currently, we support storing data to your local file system and to an AWS S3 bucket, but we will keep extending the list of storages, including the ability to support writing to a database. And reuse things like the file readers, unit converters, and our quality checks. We provide this set of abstract classes that can be extended and contributed back. So they're external to the pipeline, but they're used in your pipeline. This way we can share them across multiple projects. So the file handlers, they just deal with reading and writing specific file types. And we have support for CSV, ncdf, and we're working on Parquet format. But we'll keep adding more as we go. And then converters handle unit conversions, and we currently have time converters for both string format and timestamp format. And we have a default converter that works with any units that are UD units 2 compatible. The quality checkers perform specific QC tests on variable data, such as checking for missing values or values not being monotonically increasing or decreasing. And quality handlers define how the pipeline should handle QC failures, such as do an interpolation to fill missing values or possibly fail the pipeline if the failure is severe. So which of these classes that you use for your pipeline are declared in the pipeline config file? Okay, next animation, thank you. So finally, we also know that every ingest has special one-off circumstances, or not everyone, but often there are special one-off circumstances that you need to deal with, such as making instrument corrections or adding new variables that you derive from other variables. And so in order to support this, we provide pipeline code hooks after each phase of the pipeline so that users have the ultimate complete control over the data sets that are produced. Then, next animation, to make it easy to get started, We wrap the config files, the pipeline code with the stubbed out hooks, the example file handler, converters, quality checkers, and handlers, and some sample data into a GitHub template repository that works out of the box. That way you can jumpstart your development. Currently, we have 2 templates, one for local file system storage and one for AWS storage. But we definitely plan to keep increasing the number of templates and support templates for different data models as they are defined. And just a note about the AWS template, it requires AWS knowledge to get started. So if you are interested in deploying to the cloud, please contact us and we'll definitely help you get that going. That is my introduction. Now I'm going to hand it off to Max, who's going to give you a hands-on demo of how he used the local pipeline template for a real data use case. Thank you, Max.
Thank you, Karina, for the introduction. All right, so we're now moving on to the live demonstration portion of this presentation. And so to start, I just want to give a brief overview of what we're going to be doing. And so what we're doing is showing an example of a tstat ingest pipeline using one of the template repositories that Karina talked about. And so what we're doing here is we're just going to show how to get started. We're going to show the customizable components in a little bit more detail. And we're going to run the pipeline on the sample data. And so what sample data are we using? We're using data from the Atmosphere to Electrons program. And they have a buoy that's located in Morro Bay, California. And on that buoy is a LiDAR instrument that measures wind vectors at a couple different altitudes. And that instrument produces files, and one of them is the SDA file, which is 10-minute averaged data. And so the goals of this ingest are to embed metadata into the output file for the ease of use of data users. We want to perform some quality checks and controls to assess the data quality and handle it. And we want to visualize some of the processed data. All right. And so to get started, these are the 4 basic steps. So step 1 is to get a template from GitHub. And so if you go to github.com/tstat/template repositories, this is a repository that tracks other repositories that we've developed that are templates that you can extend. So step 2, once you've installed one of those template repositories, is to install your dependencies. So if it's just tstat, then you just do pip install tstat. Step 3 is to configure your template to meet your particular data needs. So this is where you'd customize the config files or write your own file handler or customize the pipeline, as Karina mentioned. And then step 4 is to run your pipeline. All right, and with that, I'm going to actually leave PowerPoint. All right, there we go. And I'm just going to go to this link, and I should have it pulled up already. Okay, so here's the list of template repositories. Currently, we just have the 2. So there's ingest template local, which is for running on your own file system. And there is ingest template AWS, which, as Karina mentioned, is for running on AWS Lambda. And this is a little bit more involved. So what I'm just going to do today is use the local template. And so to get started, all we have to do is go to this link. And this is just the GitHub repository. And the special thing about it is you can click use this template. And what it will do is allow you to clone this to your own account. So I'm just going to call this tstat ingest pipeline demo. I'm going to make it public, but don't count on finding it later because I will probably delete it. And what I'll do is I'll just click create repository from template. And this is pretty quick. All right, and there it is. It's in my account. It's here. And so what I'm going to do next is I am going to download this to my own machine. So I'm copying this link. And I'm going to open up a terminal, which I already have pulled up. I'm going to put it in a location where I want to keep this. I'm just going to do a git clone and paste that link. All right, so now this is on my own machine. I can see it here. And what I'm going to do is I'm going to open this up in Visual Studio Code. That's my code editor that I like to use. And it works well with some of the components that we have defined here. So I'm going to do that. All right, so here it is. So we can see the different components of this template repository. So we have a config area, which has our pipeline config and our storage config. We have our data that comes packaged with the template repository. And this is actually the data that I mentioned earlier. So I will just be using this. We have some Python classes. So this is where we do our code customizations. There's a tests directory here, which comes pre-populated with a test that just runs the pipeline. Then there's some files, and there's our run pipeline.py, and this is our entry point. So I'm going to start with the raw data just to give a brief overview of this. All right, so here it is. This is the LiDAR file at Morro Bay. And we can see that it starts off with a header with some global attributes that describe the file. And I'm actually just going to skip most of these because I'm not going to worry about ingesting this quite yet. What I'll do instead is I'll focus on the altitudes, and I'll focus on the data below it. So I'm just going to scroll down here. All right, so we can see that this is time series data. So each row is one timestamp. And we can see that the delta between rows is 10 minutes, and it is always that way. If I scroll all the way to the bottom, we can see that this file spans an entire day. So this is just 1 day's worth of data. All right, and I'm going to just show what we have in here. So we have some temperature measurements, we have pressure, relative humidity, a couple other variables. And the bulk of the columns are measuring some wind speed properties, so wind speed and direction. And then there's like a data availability column as well, which I'll focus on a little bit. And we see that this is repeated at each height. So there's 12 different altitudes here. And there's 11 different variables at each altitude. So I think that's 132 or so columns just dedicated to the variables that are dependent on altitude. So that's a lot. That gets a little bit unwieldy to work with. So one of the things I'm going to do in this ingest is kind of condense that into two-dimensional variables. All right, and the last thing I want to point out here is just, so this second column here, this is temperature. I've fudged the first 3 data points just to show how we can account for bad data. So the first temperature is -1 degree Celsius, then it's 9 degrees Celsius, and then 60 degrees Celsius, all within the span of 30 minutes. So it's obviously bad, but we want to be able to automatically account for that. So that's something we're going to do in this ingest example as well. All right, and with that, I'm going to open up the pipeline config file. And this is the file that is going to describe what variables we want to retrieve and how they should be retrieved from this file. And so it's broken down into three main sections here. So there is the first section, pipeline, and this is just describing some metadata about the pipeline itself, including some attributes here that are used for naming the files that come out of this pipeline. So in this case, we're running at Morro Bay, so the location ID is Morro. I have a LiDAR qualifier just to indicate that this is the LiDAR instrument on this buoy. And our data level is A1 because this is an ingest. So the next section that we're going to look at is the dataset definition. And this section defines the attributes, dimensions, and variables of our output file. Sorry, let me just collapse these. All right. So the attributes, I've just set some sample ones here. They're not not too useful at the moment. But the idea is that you would tailor these to be more useful to your particular case. So for me, I just have the title of example ingest for A2E LiDAR data, just a description, a little code URL to point at the link to the code that's running this. This should actually be updated to whatever link you cloned the template repository to. So just some attributes that describe the data set as a whole. The next section is dimensions. And so here I have time, because this is primarily time series data. And then I have height. And this is just because in the output, I want to have two-dimensional data. So data that is dimensioned by both time and height. So the wind speeds and the wind directions. And so the variables that I'm going to ingest are time, height, wind speed, wind direction, data availability, and air temperature. And so I'm going to look at time first. So time has a couple different sections of its own. So it has an input section, has dimensions, it has a data type, and it has some attributes or metadata. So the input section is where we define how the data should be read in from the input file and converted to the output. So in this case, we have an input name of timestamp, end of interval, and that's because that's the exact name of the column in the input file. Then we have a converter, and this is being run to parse this string as a Python datetime object. And so what we need for that are a time zone that the data was measured in, and so in this case it's UTC, and then a time format. And this describes how we should parse this string for the year, month, day, hours, and minutes. And so that's used to convert it to an object. So time is a coordinate variable, and what that means is that its dimensions are itself. So this is one of the primary dimensions of the data set, so its dimension is itself. So the next thing we're going to look at is height. And so height, this time I'm not saying it has an input, I'm just directly copying it, copying these values into an array here and defining it right here. Its dimensions are itself, again. It has a data type of int, and it has just some very basic metadata. All right, so wind speed is pretty much identical to one direction data availability in terms of its shape and how it looks. So its dimensions are time and height. And so there is some code that I have to write that'll do this. Notice that it doesn't have an input, but this is how we specify that we want to condense the output or condense the input into a single 2D variable. All right, the last thing that I'm gonna look at in this data set definition section is air temperature. And so we can see that it comes from the int temp, that character is the degrees character. And so it's pulling it from this column. It has input units of degrees Celsius. Its dimensions are by time. It has a data type of float. And then it has some attributes here. And so the first couple are just useful for metadata purposes and just for the end user to understand. And this last one, fail range, this actually ties in with the quality management. And so this is used to define the minimum value and the maximum value that we define to be okay. So essentially, if the data is below 10 degrees Celsius, then we say it's bad. And if it's above 50 degrees Celsius, then we say it's also bad. If it's in between, then we say it's okay, at least for this particular check. All right, so the check that we're using is in the quality management section. And here we have a couple of different quality managers. And so each quality manager, I'm going to open up the manage fail min because this is what's going to parse this. So each quality manager defines a quality checker and at least one quality handler. And so as Karina mentioned earlier, so quality checkers are what are going to run on your input data and identify values that are problematic. And so this is just a Python class that has been written inside of tstat.qc.checkers. And what it does is it looks at each variable's fail range attribute and takes the first of the two values there. And for each value in the data file that is below one of those values, we say it's failed that check. And the action that is taken when we fail a check is defined by the quality handlers that are in this quality manager. And so this particular quality handler, sorry, is going to record the quality results in a ancillary QC variable. And that will become a little bit more apparent what I mean when I run this in a second. But so what we're doing here is we're just saying that if we fail the fail min check, then we're going to create an ancillary QC variable that has the same shape as the data that we ran on. And for each index in the input data that failed, we will set the value of 2 in the output QC variable and give it an assessment of bad and say that it's failed the fail range check. All right. So that is the pipeline config file. I'm going to leave that there. The other config file we're going to talk about is the storage config. And so this file is essentially just telling us where we are going to store the data. So I'm going to keep this in a storage file that's relative to the configure, it's on the same level as the test stir here. And then we also define some file handlers that are used to read in the input file and output the output file. So in this particular case, we're reading in files that end in .sta, and we're writing out files that are in the netcdf file format. And so these are, again, Python classes that you can just pass parameters to. And so this particular case, these are the parameters that I'm passing. Okay. So the last thing I'm going to show briefly is this pipeline area. And so I'm going to start with this one, pipeline.py. And so this is the code that we are going to actually run. So it extends the tstat ingest pipeline class. And I've defined a couple of code hooks. So in this particular case, the customized dataset hook at Morabay, there was a, well, first, sorry. So right here is the logic for compiling the 1D variable columns for wind speed, wind direction, and data availability into 2D variables. And then right here is just some logic to apply a 180-degree calibration factor to the data if it's running at Morabay. And this is because some of the cables that were installed for the instrument that measures wind direction were installed backwards. So it actually reports it 180 degrees off. And then the last thing here that I'm going to look at is just the hook to generate and persist plots. And so this is where you just write some Python code that operates on an X-ray dataset object and writes and persists some plots. And we have this example to help show that. Okay. We also define a file handlers.py file, which just comes with a dummy file handler to just show the template for writing your own. And we have the same thing for quality checkers and quality handlers. None of these are currently used in this example. This is just to show how you could do it yourself. All right, and so with that, I am going to actually run the pipeline. And I've kind of taken a shortcut. I've already installed tstat. I'm using an Anaconda environment to do that. It just makes it a little bit easier. All right, and this takes a couple of seconds. I'm running on my laptop, so it can be expected. Okay, so it's done. And so what we've done is it has run and it has created the storage file, the storage directory. And what that has is two folders. One is the 00 data level. So this is the raw data that has been renamed according to our data standards. And then we also have a folder with the A1 data level. And this is the output of our ingest that we just ran. So here we have our netcdf file. We have two plots. And so I'll open up one of these plots. So the first one we'll look at is the wind speed and direction plot at Morabay on the 1st of December, 2020. And so here we have two subplots. The first one is the wind speed and direction, with X being the time axis and the Y is height. And the second subplot is data availability. And this is a quality metric that was built into the data set from the onset. That's just kind of like a quality metric. So when you have low data availability, it means your data is likely missing. And so indeed we see that trend here as well. Right. And the second plot to look at is just some wind profiles at varying altitudes. So same thing, X is the time axis, Y is the, Y is the speed axis this time. So we can just see that the higher altitudes are generally have higher wind speeds. Okay, and the last thing I want to do is to open up this data. I kind of want to open up the actual netcdf file. And so what I've done is this repository comes with a Jupyter notebook. And you can run this notebook to view the output data and do whatever sort of extra analysis you want. And so here I've just done that. And so we can see how our output data looks. So we have our height dimension, we have our time dimension. We can open this up and see the actual data values just by clicking on these icons. We have our air temperature, our wind speed, our wind direction, and data availability. And for each of those, we also have a quality check. This is because, sorry, a QC variable. This is because in the pipeline config file, there were a couple checks that I didn't show you. But the one that I did show is for the air temperature. So here we have the QC air temperature displayed. And so we have 3 tests that were run. So the first was just to check if the value was missing. I didn't show that. And what I did talk about is if the value is less than the fail range. And so then if it is less than the fail range, then we have a value of 2 or a mask of 2. And so we see that the first 2 values are were less than the fail range. And so they were set as 2 here. And that indicates that there was a quality problem. And then the next one is its value is greater than the fail range. And so this corresponds with the value that was 60 in the input file. And so we can have a reproducible record of our data quality in these ancillary QC variables. And at the bottom here, we also have our global attributes that were displayed also in the pipeline config file. And so this is our embedded metadata that describes the data set as a whole. All right, and the very last thing I'm going to do before I open up the questions is to just show this routine for plotting QC variables. And so here we see that the bottom subplot is the test values and their meanings. So test 2 is the value is less than fail range. And we see that the first 2 points here are red, meaning that they failed. And the third point here, the third test, we see that the third point failed greater than the fail range. Okay. And that is where I'm going to leave it for now. So are there any questions?
And before we go into questions, I also just want to say that we will be continuing to develop shortcut methods for different types of plots. So we'll try to make the method that Max just showed you is an easy way to just make this QC plot, but over time, we definitely will be contributing more plotting routines, easy shortcut methods to make plotting easier.
Okay, if there are no questions, I'm going to move back to the PowerPoint.
So, Karina, this is Chitra. We had a couple of questions that were sent to us by email ahead of time. Maybe one of the questions, we can answer a couple of questions now, or do you want to finish the slides?
I think it's great. We can answer them now. That sounds great, Chitra. Thank you.
Yeah. So the first question was, can we generate several netcdf files in the output? For example, 1 file per month or 1 file per year?
You can definitely generate several netcdf files in the output, but for an ingest, the output that you produce is going to be based directly on the input that you had. So if you send it a month worth of data and then you want to produce a daily files and a monthly file, you can totally do that. You would probably add that in the finalized data set hook of the pipeline. Then we have our storage class has methods to be able to store files. So you can store any additional files that you create, and it'll automatically, if your data set that you create has the, so like right now the pipeline is going to produce 1 data set, but you could copy the data set and change the metadata in the finalized data set handler or hook, and then you could automatically say, write this one, write this one, write this one with the storage, and then you would end up with the corresponding multiple files. If you have different input files that are from, that are totally from a totally different data set, then those we would want to put together with a VAP. And that is what we're going to be supporting next year. So that would be where you would have, like, say you have different input files and they're on totally different time resolutions. You would want to ingest those separately. And then later you could add a VAP that could combine them together and make summaries based on those.
Great, thank you. I think the next question also is related, and you may have partially answered it. So can we complete missing values of a data set already post-treated by the data ingestion pipeline by values from another data set? So, or generate a data file from two sources, basically. You're so using missing values, you set missing values through the pipeline, but now you want to take values from another data set and replace the data from the other file with the data from the second data set. Does that make sense?
Yes, yes, it does. So for this first version, when we have the pipeline runner that Max demonstrated, it can take one or more files. So you can pass it multiple files, but we assume that all those files can be homogenized onto the same time grid. So if they're really, really different, then we will add support for fetching other data sets that have already been processed as part of the VAP framework, but we don't have that in there right now. So right now, if you do have multiple files that you want to send in together, also if you have files that are accessible via HTTP URL or some other URL, you're free to access those directly in your pipeline code. But yes, in the customized data set, you can add new values, you can change values, you can do whatever you want. That happens before you do QC, or in this case, after we run the QC, you can, in the finalized data set method, you can go ahead and look and see if you didn't like the auto QC values that were picked, you can go ahead and override those.
Okay, thank you. So two more questions. One is, if we have, for example, wind data at 10 hertz, is it possible to apply quality checks and then generate several ncdf files with the time resolution of, say, 1 second, 10 minutes, and 1 hertz by implementing the hook, one of the hook, where we could customize the output resolution?
Yes, it is definitely possible as long as you have all of the data that you need originally that was sent into the ingest. In the finalized data set hook, you can take the data set you have. So say your data set was all 1 second measurements. You take that data set and then you could copy it, and you could create very easy to create averaged values using the Xarray rich API and the NumPy API on the data values. So yes, you could create, so then you would, in the finalized data set hook, you'd have your original data set that the ingest produced, which was at 1 second, and then you could copy it and then reduce it to 10-minute and 1 hour average. And then using the storage API, you could write those additional data sets to file, and then your ingest would produce 3 different files.
Great. So the last question is, can we use as input raw data directly from a database like MySQL?
That is a great question. Definitely over time, you want to be able to support connections between more than just files. But for right now, we're just starting with file-based connectors. So if you do have MySQL data, if you can dump it to a file, then we could totally use a handler that could read in the file and be able to parse it. And whether if you dump it to CSV or however you want to do that, then you could be able to bring it in that way. But right now we don't have direct connections directly to databases, but we would definitely want to do that, and especially for the output, because the storage is the key. You want to pick the right storage and the right file formats and or formats on the back end to support the type of data lake that you're building for your community. So that's going to depend on the type of tools that you want to use to perform these big query searches across all your data. And there are a lot of options available. If you have NetCDF file format, you can use the HDF high performance file system to be able to do big queries. If you write out your output to Parquet and it's sitting on AWS, you can use Amazon's Athena query language to be able to query across all your data sets. You could also, when we add our SQL type support, you could have it output to like a time series database if you prefer to do your queries that way. And so we want the pipeline to be super flexible so that each community can set that up in the way that best meets their needs.
Great. That brings up the next question posted on the chat box is, what database does TSDAT already support, which we don't right now, unless you dump it to a file, but what are you considering to be integrated into the framework? That's a great question.
What are you what? Sorry.
What database are you considering to be integrated with the framework?
That's a great question. And I am not the expert on time series databases. So we definitely would want to meet with the community, and I would say our priority, we've worked a lot with databases. And so our priorities would be talking to the community members and different projects and see what the needs are. And then we can basically want to be flexible enough that we can support whatever people need. So we'll just.
That's an excellent answer. But if you do, Vinay, if you do have suggestions, please send us an email as well. If you're working with a particular database, we can see if we can use that as a prototype and use that as an example.
Sure. Quick comment is I had explored time series in database InfluxDB. I think that's a popular one. So I think that's something could be interesting to us.
Okay, and what domain are you working in?
So this was for transportation related data.
Okay, great. And we do support, we do have our own portal to support transportation data. I don't know if you've heard of Livewire.
Yes.
So great. So we are potentially going to be using the same data ingestion pipeline to standardize transportation data. So this is great. Good to know.
Sounds good.
Thank you, Vinay.
Thank you.
Another question, Karina, is in input configuration, do you have to configure each variable / column separately, or can a set of common configurations be applied to multiple variables?
Oh, that is a great question.
Great question. Yeah.
Yes, we actually have, we didn't go over it because we don't have a ton of time, but we do have a default section that you can put in the variable definition. So if you define defaults, then all your variables are going to by default inherit those values, and then you can override them for a specific variable if you want. And in addition, we have several tickets that are currently on our to-do list for keep adding improvements, because the goal is to make this easy to use. Another one of the improvements we'll be adding to with all the global attribute metadata is a special variable flag that you can put in your config file that tells us that I just want to pull this values directly from the input so that the users don't have to copy it. And so we're trying to keep adding features so that the users have to write less and can get this completed with the least amount of work.
Is that true of QCs too? So can you apply the same QC for multiple variables?
Yes. Yeah, we have special flag words you can say apply it to all data variables. You can say apply it to all coordinate variables. You could say just apply it to this one variable, or you can give it a list of variables. So when you define a QC test, you can explicitly say which variables are going to be included in that test.
Yeah. I'm going to pause right now to see if anyone else has any question. Great. So I think Karina has a couple more slides. Is that right, Karina?
Yes. Yes, I do. So let me see. I wanted to we wanted to give you an overview now, kind of, just so you're all aware of what our plan is for the roadmap for developing TSDAT. So the main things to highlight here is that next year, we're really going to be working on our VAP framework, which is the aggregation and transformation across data streams. That'll also add the ability to be able to retrieve data from existing data that's already been processed and stored. And then in addition to that, starting next year, we're going to be working with the MHKDR team to be able to integrate the TSDAT pipelines into MHKDR so that new data, specific types of data that are coming in to MHKDR can be automatically processed and converted to standard format. And then we also will work with them as part of their design for a data lake, because that is our plan, is that all this data that gets converted to standard format, it will be put into a data lake with a big query capability so that users will be able to do these queries across multiple data streams. And that's going to really support our bigger scale analytics. Then we're also going to be continuing, that I think I have spanning over several years for the rest, hopefully the rest of the life of TSDAT, we're going to be continuing to support and develop these data models. And the data models, in particular, you want to create templates like Max showed you. You want to have one for different data models. And the cool thing about that is, if we have like a data model for wave energy conversion, and we already know what the IEC standards, and we have this wonderful MHKit library that has all these computations already in there, we can actually make a template that has all the calculations pre-filled out for you, so that I think those kind of things will make it way easier for people to get the analytics done. And so those are our goals, is really to focus on, once we get the base VAP framework done, of course, we'll continue adding improvements and bug fixes along the way, but then really to be able to support repositories and data lakes, and then get these data models in there. That's kind of our long-term vision for where we want to go with this. Okay, so next slide. So that is pretty much what we had covered for today. Of course, if you have additional questions, feel free to ask them at any time. We really thank you for participating. As we said, we're just getting started with this project, so it's very new. We have lots of things on our to-do list, lots of things we'd like to do. And we, it's just really been Max and I, so we would love to get additional contributors. We would love to help you with your project work. We really are excited to find new early adopters that can help us, and we can help them, because it really helps us to flesh out features and how we can make the pipeline easier to use. So we've updated our mailing list. It's tsdat@pnnl.gov. So please feel free to contact us anytime if you have questions, or you have an actual project that could use this. If you have a data repository that you would like to start standardizing so that you can get it in a data lake, we'd love to work with you. So please contact us at any time.
Thank you, Karina and Max. So just so all of you know that this has been tested for the wind program and in the buildings program. So we have actually used the code to standardize some of the data. So it has been tested. So we have great confidence about the code. So one of the last question that has come in is, are you looking at supporting AWS Lambda or something similar? And we have prototyped this pipeline. Maybe Karina can speak to it in using AWS Lambda. Go ahead.
Sure.
Karina.
Yes. So we do have a Lambda template that will run out of the box if you change the configuration properties to use your account and your S3 bucket. It's just the initial stages of a first Lambda template to get you going. But of course, you can modify and tweak it as needed depending on your environment. So the way that template, yes, because we really, there are a lot of tools, especially if you're developing a data lake. There are a lot of tools in the cloud that help you get started. And so we definitely want to support AWS. And so the way this template works is it assumes that you have an S3 bucket where all your incoming data is being passed, and it can be it could be any type of data, because this particular template supports multiple pipelines. So basically allows you to be able to invoke multiple pipelines and control them through a single Lambda function. So incoming data comes into a S3 bucket, and then it goes to the Lambda function, which decide there's like some regular expression pattern matching to decide which pipeline should be the one to service the file request. It processes it, goes into an output S3 bucket, and then the output S3 bucket then is there to be able to be connected to any type of cloud utilities that you need, including like potentially like Athena for being able to query your data across files. And so you can modify the so it's a default template, and it uses command line tools to be able to deploy. So you can deploy it from your desktop. And in the README, there's like the requirements that you have to have, which there are, you know, several requirements for the cloud. You have to get like their command line toolkit, and you have to get an account and those kind of things. And you have to have permissions on your account to be able to create new resources. But then you could actually just run the deploy right from your desktop and be able to deploy that whole stack of resources out to AWS using their CloudFormation API. And so oh, yeah.
Yeah. So Dustin, if you do have projects that would want to use this, please reach out to us. That brings up another question. Max, would you be able to show the documentation page? Yeah, if you click on it.
Yeah. I think I actually need to exit this, otherwise it will keep sharing.
Okay, so there's one more question as Max brings this up, Karina. In certain domains, the QC can have dependencies. For example, measurement X1 at timestamp T is good quality, while when it is less than value of X2 at T. Can the QC support these? Also, how about cross-time dependencies? X1 at T is good quality, while it is less than value of X2 at timestamp previous to T. So basically, you know, one variable's QC is dependent on another measurement, or maybe one timestamp previous to the current timestamp. Does that make sense?
Yes, it does. And our framework does support that. So when you make a QC checker, you get past, you have the whole data set you have access to, and then you get past the name of the variable that you're checking. And so it is very, very easy using the X-array and the NumPy APIs. You basically get a whole data array of all the values for that variable. And then it's really easy to be able to check the values. So we've actually done some tests where we check the value against the value of another variable, or you can do like the standard deviation of all the values of your variable and then check to see if you're an outlier. And one of the things that we really like about the X-array and the NumPy API is that it's really like you hardly have to write any code, and it's really clean and easy to read. So yes, we do support that, and we feel that it will not be a painful process to add to, and we hope that our community, as we would love to have more QC checkers for the standard types of checks. And we just have like the bare bones in there right now. And so that is something we are really looking forward to having the community contribute more for us.
Great. Thank you. I'll wait maybe 10 seconds to see if there are any other questions. Great. Thank you all for joining. Thank you, Karina and Max, for the webinar. And we will send, Haley, we will soon send a link to the recording if you want to share. And please reach out to tsdat@pnl.gov if you guys have any questions. Thank you all.
Thank you guys so much.
Thank you, everyone.
Bye.
Bye.
Thank you. Bye.